you again, everybody, for joining us today. My name is Joshua Austin. I'm a senior applications engineer with Toshiba. I just celebrated 15 years with the company. Today we're going to be spending 45 minutes to an hour talking about predictive monitoring and protective features for low voltage drives. And again, we'll primarily be answering questions at the end of the presentation. And so we'll go ahead and get started. So as we look at the agenda for what we're going to try and cover today, we're going to be looking at protection features for the drive, the adjustable speed drive, ASD. Sometimes you'll see VFD, VSD, a lot of interchangeable terms. Look at protection features for the motor, protection features for the driven equipment or the process, and then finish with maintenance and monitoring capabilities. So from a protection standpoint, there are multiple layers or priorities, if you want to look at it that way, in terms of what the VFD protects. So the primary priority or layer of protection that the VFD is going to provide is going to be to protect itself. The drive wants to protect itself from a catastrophic failure. The second layer of protection is going to be the motor that the VFD is operating. And then the tertiary layer of protection is going to be the load or the driven equipment. So when we look at the ratings or specifications for a low voltage adjustable speed drive, what you'll see here are some of the common specifications maybe listed on a data sheet or a brochure. The first being the voltage rating or the voltage tolerance for the VFD. So we're going to have an input tolerance rating, typically plus or minus 10%, and also a tolerance for the input frequency as well. So the voltage rating is primarily focused around the capacitors that are used inside the VFD. So with low voltage drives, the topology converts AC to DC, and then we filter the DC waveform using electrolytic capacitors, and then we use IGBTs to recreate the AC waveform using PWM, pulse width modulation. So that voltage rating or specification is going to help us to protect the components inside, mainly the capacitors, and the drive is going to protect those from failing. And then we also have current specifications. So inside the VFD, we have diodes or silicon control rectifiers or IGBTs, semiconductor devices that have current limitations. And the drive itself will have multiple different current ratings. So it will have a continuous current rating. It will have a overload rating typically for 60 seconds. And then it will have also a instantaneous overload rating as well. Now, different drives or different manufacturers may also have different duty ratings. So that one VFD, one drive, one ASD may be able to be configured for different current ratings and different power ratings depending on the selection. So for example, with our AS3 product, we have what Toshiba calls heavy duty and normal duty. And typically that's referring to the 60-second overload. For heavy duty, going to be 150%. And for normal duty, it's 120%. And some manufacturers, the normal duty or standard duty will be 110% overload for 60 seconds. So we talked on the last slide about the voltage rating or specification. And there are some applications where the motor actually generates voltage back to the drive. So that's not always the case, and the vast majority of applications, the motor is going to be a consumer of power. But there are applications or maybe cycles in the application where the load is going to cause the rotor to spin faster than the magnetic field, and it's going to reverse that flow of energy, and so the motor becomes a generator of power. And so there's a list here of different applications where we may see that. A downhill conveyor, pump jack, centrifuge, or any other application where we may have a quick deceleration that's required. One thing that I want to note here on the bottom left-hand corner is that we have a note regarding these different topics in connection to our AS3 general purpose low voltage drive, where we've got the parameter that can be used to adjust these features, and also the manual section referencing additional details if you want to read further on those topics. So each of the features that we talk about will have a reference down at the bottom left-hand corner. Now we know that the capacitors have a voltage rating limitation, and we know that there are applications where the motor is going to regenerate energy back to the drive. And so we want different means of operating in those applications. So what we need is a way to protect the drive and to be able to dissipate or mitigate that regenerative energy that's being created by the motor. One of the more common ways of protecting the drive is to use dynamic braking. And in this setup, what the drive does is it utilizes a 7th IGBT to take that excess energy, and we short it across a power resistor, and that energy converts from electrical energy into heat. So now one of the things to look at is not all low voltage drives come standard with an IGBT7. So that may be an option, or in some drives, it may not have that as an option. When you look at selecting a dynamic braking resistor, you want to make sure you follow the minimum ohm requirement that's listed in the product manual. And then when looking at sizing, you have to consider the duty cycle and the amount of power that's being regenerated by the application. So duty cycle referring to how often that the resistor is going to be needed to dissipate that energy. One thing to note also is that those dynamic braking resistors, because they do get hot, are typically installed outside of any type of drive panel or industrial control panel. Some other, mentioning some example applications could be a punch press, pump jack, or any application where you have a quick deceleration. One other means of protecting the drive from increased voltage on the capacitors is what we refer to as flex braking. So there may be applications, and we try to show an example here in the graph where, as in this specific example, is looking at a motor that is decelerating. So when the motor is decelerating and the drive is reducing the output frequency, we can see that the DC voltage is increasing because of the regeneration from the motor. And so what the drive can do is the drive can increase that deceleration time in the hope or the effect that it will reduce or eliminate the regenerative energy that's being created by that motor. We've also used features like this on pump jack applications just to increase the speed of the motor. Even though you're not decelerating, when you increase the speed of the motor to match the actual rotation speed, then you're decreasing the amount of regenerative energy that's being created. Input phase loss. So most of the low voltage drives that we sell and support are 3-phase devices. We do have a couple of drives that support single phase input without modification and generate 3-phase output. But all of our drives are 3-phase output drives. But there are applications where you need to utilize a single-phase input because that's all that's available. But if you do have 3-phase power and you lose one of those phases, that's going to cause an increase of current on your remaining phases. And so you want the drive to shut down before any damage is caused to the drive. So by default, the drive will fault or trip whenever it detects an input phase loss. And then when needed in the appropriate applications, you can disable that protection feature so that you can operate with only single phase input. Now, when you do use single phase input, we do recommend oversizing the drive so that the input rectifier section can handle that reallocation of input current. We do have documentation on that. If you would like more information, you can let us know about that. Now, all of the semiconductor devices inside of the drive are mounted on an aluminum heatsink, and we use air cooling, a blower or a DC cooling fan to force air across that heatsink to cool off the semiconductor devices. Now, we also have an ambient temperature rating. For example, the AS3 is rated up to 50 degrees C ambient without any derate. And so that's going to be the ambient temperature. The actual temperature of that heat sink is going to be much hotter than 50 degrees C while it's operating at full load conditions. With the AS3, as opposed to legacy drives, we have additional failure detection built into the cooling fan circuit. So what that allows us to do is as soon as that cooling fan fails, we can trigger a fault on the drive so that the drive shuts down and does not have any excess wear and tear from operating at high temperatures without the cooling fan. In cases where you have to continue operating, possibly that failure detection circuit is not working correctly and the cooling fan is actually still working, or maybe you're utilizing an external cooling scheme to be able to cool down the VFD so that you don't have to shut down operation. You can turn off that failure detection so that you can enable the drive to run. There's still overheat protection. This is just specific to the cooling fan failure detection. Speaking about overheat, so we have 3 different levels to look at when we talk about overheat. So we have our ambient temperature rating of 50 degrees C, and depending on the model of VFD, and when I mean model, I mean different horsepower ratings have different allowable temperatures that we monitor on the heat sink. And so for each model, it's going to be different. But what's the same is the different levels or thresholds of separation. So during normal operation, there will be no alarm or fault. But once we enter that alarm condition, we can stay in that alarm condition up to 5 degrees higher, and then the drive will fault. So once the drive faults on an overheat fault, then the temperature has to drop down 10 degrees Celsius lower from the fault condition in order for the drive to be able to reset that fault, and then continue to try and operate that motor. Okay, moving into the second layer or second priority, looking at the motor. Most applications, we have one drive operating one motor, and in that case, the drive, the VFD counts as overload protection for that motor. If the drive can be used to operate multiple motors, The only difference is that the drive can no longer count as the overload protection for those individual motors. So individual overload relays or protection will have to be installed if one VFD is being used to operate multiple motors. So on the screen, we have an example of the overload curve. So an overload condition, and we also have a table here showing different points on that curve. So for example, if you're using a heavy duty AS3, you can actually operate at 110% continuous current without ever tripping or faulting the drive on an overload condition. Now, you may want to protect the motor more with a stricter overload curve, or if you exceed 110%, you'll notice that as the curve increases, the allowable time decreases. So once we get up to 150%, it's 60 seconds, or even less time as that overload percentage starts to increase. The drive is also going to have an overload stall function. And what that allows you to do is, especially on variable torque applications, if you enable this stall function, the drive will try and prevent the motor from going into an overload condition. So in variable torque applications, we know through the affinity laws that the amount of torque or power is directly related and proportional to the speed of that motor. So if we can reduce the speed, we can reduce the torque, the current that that motor is drawing. So an overload stall function is there to try and protect the motor from being in an overload condition. Also, when it comes to overload protection, the motor is going to have a turn down ratio. So the turn down ratio is going to describe the speed of operation where the motor can still run at full load conditions and still effectively cool itself. And that turn down ratio will typically be different for constant torque applications as opposed to variable torque applications. And so the drive can account for that turn down ratio, and that can be programmed into the drive. So if you have an application where there's going to be a large amount of operation at low speeds, then you can still make sure that you are adequately protecting that motor from an overload condition. Now, looking at what we call motor shaft fixing control, there are applications where this actually applies to a couple of different things. So the first one is where the motor may freewheel when it's not being operated. And so what happens in these applications where the motor is spinning during non-operation and the drive starts to try and control that motor, the drive is assuming that that motor is at zero. And so actually, I got that confused. That's actually a later slide. But for the motor shaft fixing control, when we don't want the motor to spin, we can actually stop that motor from spinning. So we can ramp down the motor. And then when we get down to essentially 0 hertz or something a little bit higher, 5 or 10 hertz, we can actually grab that motor shaft and we can prevent that motor from rotating. So there are applications where you may not want a pump or a fan to operate or spin when the drive is turned off. And the second thing is going to be that this can be an option to reduce condensation in that motor. If you have a critical application where you're experiencing condensation, we would recommend a motor space heater circuit. But if you just want a redundancy or a backup, you can use this DC voltage applied to the motor windings to generate a small amount of heat to reduce condensation. The only caveat is if the drive loses power or experiences a fault, then the drive has to run the motor again and then stop before it will start applying that DC current again. So in critical applications, we would recommend a true motor space heater. So this is where I got a little bit ahead of myself on the last slide. So catching a spinning motor, or sometimes called a flying start or catch on the fly. This happens when, in multiple scenarios, actually. It could be because the drive faulted and the motor is coasting to a stop. It could be because the VFD lost power and the motor is coasting to a stop. Or it could just be that there is an outside factor that's causing the motor to rotate prior to the VFD starting the motor. And so what we can do is we can, prior to outputting a frequency to the motor, we can detect the direction and the speed of operation of that motor and match it with the output frequency. And what this does is this prevents stress and overheating and overcurrent conditions on the motor. So if the motor is already spinning when the drive goes to start and the drive assumes that it's at a standstill, then there's a large difference between the rotor and stator magnetic fields, and that leads to a high inrush of current that typically a drive is trying to eliminate. But this is a feature that would have to be enabled or turned on so that the drive knows that this motor may be spinning prior to receiving a run command from the drive. On the output side, we talked about input phase loss earlier. Now, on the output side, we're trying to protect the motor. So the same way on the input side, if we lose an output phase, because we are using 3 phases to control whether it's an AC induction motor or a permanent magnet motor, we need to know and we need to shut down the drive when we lose a phase so that we adequately protect that motor. One thing is that this feature is actually disabled by default on the Toshiba drive so that we can operate the drive without a motor connected. So this is actually great for commissioning and troubleshooting to be able to run the drive without a motor connected. But once you have your motor commissioned and operating, we do recommend to enable the output phase loss feature so that you can protect the motor. In certain applications where you use advanced motor control like vector control or automatic torque boost, the output phase loss function is automatically turned on and you don't have to go and set that. Alongside output phase loss, the drive will also protect the motor from ground fault conditions. And this may be, the drive will use a short pulse every single time it goes to start the motor to try and detect if there is a ground fault short circuit. And both of these things, output phase loss, ground fault detection, or a short circuit in the motor, those things may also not be true of the motor, but it may be true of the cables that are going to the motor. So the drive is trying to protect that whole entire system. Looking at voltage compensation. So I think everybody's familiar with the fact that input voltage is likely to vary either throughout the day or throughout the week, or depending on the operation of the facility. The input voltage can go up or down depending on the loading of the transformer or the incoming utility supply. And so we have different options or selections how the drive can react to different voltage conditions and try and protect the motor and try and protect the operation of that motor. The ratio of voltage to frequency is very important for the motor to be able to maintain the rated torque for its operation. So this parameter and this feature allows us to protect the operation of that motor regardless of the speed and regardless of the input voltage condition. When it comes to motor thermal protection, the drive doesn't have any type of thermal sensor built into the drive. That sensor has to be embedded inside the motor itself, whether that's PTC, positive thermal coefficient, or RTD, resistive thermal detector, temperature detector, so that those devices can actually be wired in from the motor to the drive itself, or you can use separate motor protection relays if you want. But for example, we've been referencing the AS3 low voltage drive throughout this presentation. We have one standard analog input that can be used for motor thermal protection. And we also have the option to add additional terminals that would allow up to 2 additional inputs for motor thermal protection. Moving into our next layer of protection, being the driven equipment and the process, we're going to look at multiple features that try to prevent mechanical stress, or even just try and reduce the amount of downtime that a system is going to experience. Because we know that not only is the equipment have a cost associated with it, but we know that the operation and runtime has a certain cost to it as well, right? When there's downtime, it's costing money when you're not able to run. So the first function or feature that we'll look at is our coast to stop feature. So when you stop the VFD, the most common or the default way of decelerating that motor is what's called a controlled stop. And that means that you're going to control the frequency from the operating frequency all the way down to 0. And so you're going to control the deceleration of that motor. But in a coast to stop, the VFD will essentially let go of the motor, and it will use the inertia or friction of the rotation of the rotor to stop that motor over time. So it's freewheel. And this is going to be a potentially in some applications a much smoother stopping process, and especially in high inertia applications, you will decelerate the motor up to a certain point, and then you will let go of the load and let it decelerate on its own freewheeling. So there are multiple ways to achieve this. It can be done by programming one parameter to coast after a certain frequency, or you can use your digital inputs or communication registers to initiate that coast to stop as well. Looking at reducing downtime, we have the automatic reset function. What this feature allows you to do is it allows you to automatically reset certain faults that we have defined as soft faults or non-critical faults. And so you can see a list of these here. We have overcurrent, overvoltage, overload, overheat. So whenever these faults occur, you can program the number of times that the drive will try to automatically reset these faults and continue operation. So you can program it up to 10 times. And then after that 10th time, it will require a manual reset of that fault. So this is incredibly useful in applications where you may experience a nuisance trip that's not related to that specific VFD or motor. Maybe it's something with the process or the system or whatever it is that you know it's okay to automatically reset that fault. And so that's going to reduce having to send somebody out in person to that VFD to reset that fault. The next feature is undercurrent trip. So there are applications where the drive is controlling the motor And then the motor may be connected to a pulley or a belt that is connected to the rest of the driven equipment. And in that chain of operation between the drive and the load, something may break, right? That pulley may break, that belt may break. And so what would happen in some of those applications is the motor, once it breaks, the motor will still continue to operate, but it's no longer connected to the load. And so the current that motor is pulling is now drastically reduced. It's essentially completely unloaded. So I would expect in many applications there will also be other warnings or notifications that process may have, but it is possible for the drive to trigger an alarm that something has changed in the operation of that system. So you can have an undercurrent trip that if the motor is essentially running at low current for an extended amount of time, then you can shut down the drive. Very similar to an undercurrent trip is our sleep function. This is designed more primarily for pumps. So most pumps will have a designated or recommended minimum speed of operation, where they're typically around 20 to 30 hertz or so. And because anything below that, the pump's not really doing anything, and sustained operation will actually damage the pump. And so with this sleep function, we can program that if we are operating the pump at a reduced speed, we can shut off operation, we can shut down the pump until the demand comes back above that minimum speed recommendation for the pump. So this is going to let the drive to continue operating. It's not going to fault. It's not going to require a reset. And as soon as the demand comes back online, and then we can turn that pump back on. Jump frequencies are sometimes called skip frequencies. This is helpful when you have a mechanical or natural resonant frequency in the system. And so this may not be from, it's not normally caused by the VFD, but sometimes using a drive with a PWM output and that carrier frequency may cause it to amplify the resonant frequency. But typically, so you'll notice the increased vibration at the resonant frequency. And what these jump frequencies will allow us to do, it'll allow us to not allow the system to continuously operate at that resonant frequency or inside of a band around that resonant frequency. So we're trying to prevent any amplification of that resonant frequency, but the drive will still accelerate or decelerate past that resonant frequency. Ride through is another function that helps reduce downtime. So typically when a drive will lose power, the drive will potentially need to receive a new start command to start operating that motor. And there are some applications where not only the drive, but maybe the pump or something else in the system will need to be reprimed or restarted in order for the process to begin operating as intended once again. So if we can prevent the process from stopping during a momentary power dip, then that will reduce the amount of downtime for the overall system. And so the only thing with this is it's very application dependent. So the VFD itself, we do have capacitors inside the drive, so we are able to store a small amount of energy inside the drive, and then we're able to control that motor where we're trying to cause the motor to regenerate energy to maintain the voltage inside the drive with our capacitors and our control section. so that we can maintain control of the overall process. Heavy inertia loads will typically, it will be possible to have a longer ride through. And there are even some devices we've seen on the market where they'll actually add capacitors in connection to the DC bus to try and extend that ride through capability as well. Torque protections. So the drive has lots of different torque protections, and it's all depending on what you're trying to prevent from happening in the application, whether that, your belts are only rated for a certain amount of torque, or the gearbox is rated for a certain amount of torque, or something like that, or even that you want to keep torque over a certain amount. We can, on the drive, especially with the AS3, our latest drive, we have lots of different options to trigger a fault, to trigger an alarm, to trigger output relays. We can have that would typically be a torque trip, where we can set a hard limit where if the drive reaches this estimated torque value, because it's using the output current to estimate torque for that motor, then we can shut down the drive. But we also have torque limits, and torque limits would be where once we hit a certain torque, a predefined or programmed amount of torque, then we will adjust the output frequency so that we are not exceeding that torque limit. So lots of different options on the torque side of things to try and protect the process. Maybe different pieces of equipment should not be overstressed for a certain amount of time. There are also other features that we won't really go into today, but just wanted to make sure that you're aware of them. We have wire break detection for your current analog input signals. So if that feedback from maybe your PLC, your control system, your transducer is lost, we can shut down the drive. We also have lockout protection. What that means is you can protect the drive from somebody who maybe is not authorized from making changes on the operation of the VFD. The next one is prohibiting reverse run for applications where the motor should never run in the reverse direction. And then the last one is the emergency off stop pattern. So emergency off is going to be a stopping method, but depending on the application, we can program it to stop the motor in a multitude of different ways. Okay, going into our last section on maintenance and monitoring. First thing we're going to look at is some of the available features when it comes to monitoring the drive, the motor, and the system. So the default operation for Toshiba drive is to display the current and voltage in terms of a percentage. So that's very useful to look at. When we look about at overload condition being 150% for 60 seconds, or normal duty being 120% for 60 seconds, or our voltage rating being plus or minus 10%. It can be helpful to see percentages to see how close we are to the rated specifications of that drive. But it can also be helpful to see the display of those units and amps and volts so that we can match it to the what we may verify with an external device. We can take our fluke meter and take current or voltage measurements and compare that to the drive monitoring. Another helpful piece of information that is available when in our monitoring scheme and inside the drive is going to be our past trip data. Specifically with the AS3, we store the last 8 past trips. And so when you go into the past trip history, displays a lot of useful information that may be critical when troubleshooting. So it's going to tell you how many times that trip occurred. It's going to tell you the output frequency and frequency command at the time of trip, the direction of rotation at time of trip, output current, output voltage, input voltage, terminal status at time of trip. And then we can also, if you set up the real-time clock, you'll have a date and timestamp. And then there's also temperature data as well. And so all of this information is going to be available for each of the last 8 past trips. We do also have an extended monitoring feature, what we call trace data. And the best way to look at this is the graph here on the right-hand side of the presentation. You can see when the trip occurs, and then you can see all the data points that precede that data trip. And so what the drive can do is for 100 data points preceding a trip, we can store 4 different monitor values. By default, we store output frequency, frequency command value, output current, and input voltage. And you can use either a PLC or typically our ASD Pro PC software to extract all of those data points. And then with our ASD Pro software, you can graph those data points. And what this gives you is it gives you essentially a trend or more data of what was happening with the drive leading up to a fault. So that increase in monitoring data gives you a lot more insight into the behavior or operation of the system before the trip occurred. And ideally, that will help you lead to troubleshooting and preventing future trips from occurring. Okay, so switching from monitoring over to maintenance. When we talk about there are different types of maintenance. The first one that we're going to look at is life cycle maintenance. And life cycle maintenance means that certain components inside the drive have a designed life expectancy. And once we hit or exceed those design life expectancies, then we can replace those components. Now, design life expectancy is based on a defined set of conditions. And so at the top here, we have our defined set of conditions: average ambient temperature of 40 degrees Celsius, relative humidity 65%, load factor 80% or less, and 24-hour operation per day. So with those conditions, we calculate the expected life of these components. So the majority of our cooling fans are going to be rated for 10 years. And some of our larger horsepower drives, the main cooling fan is rated for 5 years. The power capacitors are designed for 10 years life expectancy, as well as the capacitors on the main control board. And looking at preventative maintenance, our instruction manual and documentation describes daily, periodical, or yearly practices that are best to try and prevent failures from occurring. That's going to be checking for cleanliness, checking for wire looseness. So depending on the application, if there's a lot of vibration or noise, you may need to retighten wires and connections. When you're checking on the drive, depending on your maintenance procedure or program, you may want to clear runtimers or clear the fault history and keep a log of those things outside of the drive, and it may be a maintenance program. And then the last one, this is probably the most important one on the list, is that if you have a drive that's in storage or it has been without power applied for close to a year or longer than a year, then you need to energize that drive so that the capacitors do not lose their form or performance. One other item for predictive, and this is oriented towards somebody who has more complete knowledge of the overall system. This is not going to be predictive maintenance specifically for the drive, but the drive can be used to track the number of starts. So the number of times that the motor is starting. So if you have maybe a punch press that needs servicing after every 1,000 starts, or maybe you have a lathe or something that needs to have machine maintenance after a certain number of starts, then this can be used as a predictive indication of when that maintenance needs to be performed. You can also track the number of trips that have occurred on the drive. And then the last thing that we have for predictive maintenance is going to be our condition-based parts replacement alarm. And so the conditions that we utilize are listed here. We use the cumulative power on time of the drive. So how long has power been energized for the drive? The runtime, so how long has the drive been operating a motor? The cooling fan runtime, how long has the cooling fan been running? The output current, and the annual average ambient temperature. So the drive will use all of these data points, and then based on that life expectancy that we referred to earlier, it will use our formulas to try and raise a flag or a warning that these components may be reaching the end of their design life and need to be replaced. So when you're looking at the monitor mode on the AS3, on the bottom right-hand side here, you can see that we have indications for the cooling fan and the capacitors, and those indications will go high when the drive is calculating that it is time to look at going ahead and replacing those parts. Okay, so that's all that we have today for our presentation material. And I think that Mark has probably been answering some questions in the chat. Let me pop over and see if we have any other questions that we still need to cover. Okay, so I see a couple questions that came in here. So I'll read these out. The first one is the percentage current a percentage of the drive FLA or the input motor FLA from the nameplates? So if you're looking at the output current percentage on our monitor screen, that percentage is going to be of the drive full load amp rating. So, and then we have another question here about what is the typical life expectancy of DVD-T filters. So Toshiba does not manufacture DVD-T filters. We can look into that for you if you want more information. But that is a magnetic device that does have a PCB a part of it. So I would expect that there's going to be a life expectancy for that device as well. And another question, does the AS3 have a DC choke? Do you still need a 3% input line reactor if there is a DC choke? So the AS3, every single model does have a DC choke. And what that helps is it helps to reduce the amount of harmonic distortion that's generated by the AS3. Now, the question of do you still need an additional 3% input line reactor? The drive does not need it to operate, but you may need to perform a system level analysis in regards to the harmonics present on the system to determine if additional harmonic mitigation is going to be necessary for that individual drive. I think it's very common to also install an additional 3% line reactor. One thing that you have to think about is if you have a 3% input line reactor, a DC choke, and then even possibly a DVDT filter, that means you have 3 different devices in the system that are going to impact your output voltage to the motor. So there have been small number of cases where when all of those devices are used on one system, you're not able to supply the full amount of voltage or full torque for that motor. Okay, let's see. I think we have another question here. Nope, that was just a response. So I think that's all the questions that we had today. If you still want to submit one more question, feel free to enter that. You can always respond when we send out the presentation slides if you have additional questions, even if it's not specific to the material that was in today's webinar. And with that, we're going to go ahead and wrap up. We do greatly appreciate everyone's time today and your participation and joining us to learn more about predictive monitoring and protection features for low voltage drives.